Imagine you're sitting on a train. You look at your coffee cup on the table. To you, it's perfectly still. But to someone standing on the platform watching the train zoom by at 97 kilometers per hour, that coffee is a caffeinated projectile. So who is right? The person on the train or the person standing at the station watching the coffee cup move? The answer is that both are right. The apparent contradiction comes from how motion is described from their different points of view. Let me show you something. To analyze the situation and be able to say something about position, speed, or the duration of the trip on the train, we must attach something to each perspective, in this case, to you on the train and to the person at the station. This something is called a frame of reference. A frame of reference is not a physical entity. It is an abstract concept. However, it can be associated with objects in the world, such as cars, balls, or birds, allowing us to make measurements from their perspectives. You can think of frames of reference as cameras placed at different locations in a scenario, each recording the same set of events. To perform measurements, a frame of reference must include two fundamental elements: a spatial structure, an infinite set of points in space, and a time coordinate, so that every event can be assigned both a position and a precise instant at which it occurs. Without these elements, we cannot meaningfully discuss distance, position, velocity, or any related quantity. In fact, measurements themselves do not exist without a frame of reference. Terms like left, up, or fast are completely meaningless. Now let's return to the problem of the moving train and analyze it mathematically. We have two frames of reference, one associated with the person at the train station and the other with the person traveling inside the train. Remember, our goal here is to describe the behavior of the coffee cup. Suppose the train is traveling at a constant speed v. We can ignore the y component, since the important motion occurs along the x-axis. From the point of view of the person at the train station, the coffee cup covers a distance vt at time t. Therefore, in this frame of reference, the trajectory of the object is a straight line in the horizontal direction. It is interesting because from this point of view, the cup are genuinely moving to the right direction, and we can trust in the measure of the person at the train station. The mathematical expression that relates these two frames is as follows. The distance x measured from the station is equal to the distance x prime measured inside the train plus the distance vt covered by the train. Assuming that the train's velocity v is constant, we have a special class of frames of reference called inertial frames. In this case, where the frame is inertial, the laws of physics are always the same. If an infinite number of inertial frames were measuring this event, the laws governing the system would be identical for all of them, and strange behaviors wouldn't be detected. The fact that the laws of physics are preserved in these inertial systems is a fascinating result that physicists use all the time when they are studying some phenomenon. From this expression, we can obtain the relative velocities between the observer at the train station and the coffee cup inside the train. Using a technique from differential calculus, we determine these velocities. It is simply the sum of the quantities. The speed of the cup as seen from the station is equal to the speed of the cup measured from the passenger's perspective, plus the speed of the train. This expression shows the simplicity of the relation between those two inertial frames. Additionally, we know that the cup is not moving on the table. It is perfectly at rest. Therefore, the velocity VTR is 0. This implies that the velocities of the passenger, the cup, and the train are all the same relative to the station, that is, equals v. Now that we have explored the case in which the train moves at constant speed, called an inertial frame, we will examine the case in which the train is constantly accelerating. In this case, the train is a non-inertial frame. Let's look at the diagram. Here we have the system. To simplify the analysis, we consider two assumptions. First, a particular point on the train coincides with the origin of the station frame, and the coffee cup is at a distance x0 in both frames, the station and the train frames. Second, The table on which the cup rests is a frictionless surface. This means that when the train starts to accelerate, the coffee cup will not move. This happens because every object at rest with mass tends to maintain its state of rest. This property is called inertia. Now that we have established these considerations, suppose that the person at the train station sees the train starting to move and accelerating with a constant value a. Because the train accelerates with acceleration a, we can use integration to find its position at every instant of time. We see that the train's position is a function that depends on the square of time t and the acceleration a. With this result, we can finally obtain the relation that connects the station and train frames. From the diagram, we see that the position x0 of the cup relative to the station is equal to its position of the cup in the train frame plus the position of the moving train. With this expression, we can determine x prime, the position of the coffee cup as viewed from the train. As we can see, at time t equals 0, the cup's position relative to both frames, the station frame and the train frame, is the same and has the value x0. The train then starts moving with acceleration a. Because of the frictionless table and the cup's inertia, when the train accelerates, the cup does not move relative to the station. However, from the passenger's perspective while looking at the table, the cup is moving in the direction opposite to the train, together with the station itself, all of them with the same acceleration. The passenger is seeing everything outside the train accelerating, and the coffee cup moving by itself without anybody touching it. The passenger even feels a strange pull in the direction opposite to the train's motion. This happens because he and the train are no longer in an inertial frame. The laws of physics here are not the same as for the observer at the station, and this is what we call a non-inertial frame. It is a frame that is neither at rest nor moving with constant speed, and the defining characteristic of such frames is acceleration. Even the velocity and acceleration measured in this frame are different, and they have completely different values when compared with those in the inertial frame. That's it for today. Thank you for watching. Hit the like button and subscribe for more. God bless you.